All right, hi everyone. I think this is my third or fourth video on solving the hydrogen atom Schrodinger equation. In the previous video, I talked about how we solve the radial, how we solve for the radial wave functions. Right? And if you do all of that, you end up with this table of radial wave functions. In this video, I want to talk about what these solutions look like. So whenever we solve for wave functions, the first thing we do is sketch them. It's not inherently apparent what these ones look like. So on the back of the handout that's up on Canvas, I plotted for you all of the radial wave functions. And they're shown again here. So these are labeled, right, with the orbital, 1s, 2s, 3s, 2p, 3p, 3d, et cetera, et cetera, et cetera. And I want to take a second and just ask, what do we notice about these wave functions? And so one of the first things I would point out to you was that our expectation was basically right. We said that if L were equal to 0, that is, if this were an s orbital, wave function is not equal to 0 at origin. That was our prediction. And in fact, that turns out to be exactly true, right? So you can see that all of these wave functions, all of these s orbital wave functions are not 0 at the origin. On the other hand, all of these, which have L not equal to 0, all of these, in fact, are 0 at origin. So our basic picture was right? Good. The other thing you should start to look at when you see wave functions is nodes. And you can start to count these out. I'm going to switch my pen color here. I can figure out how to do this. Okay. Right, this one, no nodes. This one, 1 node. This one, 2 nodes. 3. This one has no nodes. And so you might be tempted to say that there are n minus 1 nodes. Right? That's not consistent with this one. It has 1, this one has 2, 0, this one has 1. If you start to look at these nodes, what you might convince yourself is that these functions have n minus L minus 1. Right? So they will have n minus L nodes. And I want to emphasize to you that these types of nodes are radial nodes. Right? They are radii at which the wave function is 0. Last but not least, let me suggest to you that if you were to look at, say, across a row, so here I'm going from an S to a P to a D, it looks like, so I go across this way, wave function is spreading out. That is, a D is further away from the nucleus than an S, and that makes some sense to us. If I look down, right, 2P compared to 3P, it gets a little more confusing because these things all look like they're at about the same radius, or possibly even that the 3P is even a little closer than the 2P. We'll talk about that a little bit more, but you'll note that behavior. Right? Now, you should be able to impress your friends at the next, I would say party, but we don't have parties anymore. We have COVID-safe gatherings. So at your next COVID-safe gathering, I'm sure someone will ask you to sketch a radial wave function. So how do you do that? Right? I should say sketching R. Pick an orbital. I don't know. I hear you saying 3P. right? If I go to sketch the radial wave function for a 3p, R3p, here's how I would think about this. A p orbital. I know that this is 0 at the origin. So it's got to start there. In addition, there are 3 minus 1 minus 1 equals 1 nodes. So it's going to go up, down, and then approach 0. That's the R3p. Give me another one. 6s. Let me make these things up. This is an s orbital. So it is not 0 at the origin. It's going to start up here. And then it is going to have 6 minus 0 minus 1 equals 5 nodes. 1, 2, 3, 4, 5. Right? And it'll look like that. You should be able to sketch radial wave functions. Right? And you can impress all of your friends at the next COVID safe gathering. All right, one more thing. If I put all of this together, right, here are my hydrogenic wave functions. Psi is a function of r, theta, and phi. It's given by the product of the radial wave function and the spherical harmonic. We have 3 quantum numbers, n, l, and m. N takes on values 1, 2, 3. L is n minus 1, n minus 2, ... to 0. And L is L, L minus 1, L minus 2, ... to minus L. These 3 quantum numbers arise because of the boundary conditions in 3D space. So I have to have continuous wave functions that are normalizable, and that produces these 3 quantum numbers. The relationships that arise among them come from the separation of variables and the mathematical solutions to the differential equations that arise. Right? So 3 quantum numbers. There's actually a 4th one, but we're going to worry about that a little bit later. So on the handout, I gave you a complete table of the wave functions. So see this on the handout. This table is not in Atkins, so you'll have to look at the handout to find it. And we should go through and sketch what these wave functions look like. And it gets a lot harder to do. So there's common representations of these wave functions, which I'm showing you here. The first is as a surface density plot. So if I were to plot the 1s, this is what it looks like. Right? You can see that there's a high density of points at the origin. There's a high probability of finding it. And if I move along the radial coordinate, that density decreases, decreases, decreases. This is the 2s. You might remember that this has n minus, this has 1 radial node, n minus L minus 1. And you can sort of infer that here. High probability of the nucleus node, and there's that other little hump. This is the 2p. Note that spherical orbitals, spherical harmonics have radial nodes, not radial, angular nodes, angles at which the wave function is 0, and you can see that here. Question now is, how many total nodes are there? N minus L minus 1 radial nodes. There are L angular nodes. So in terms of totes nodes, the answer is n minus 1. N minus 1 totes nodes. This is another way that you can represent these as surface contour plots. You, again, get that same sense of things. We might shade an area in which there's a 90% probability of finding an electron or whatever it is. But you should be familiar with these types of representations. All right, that's it. And I will stop here and we will continue with the next thing. See you then.